Okay, so guys, in Unit 9, which is our very, very last unit, you'll notice this is a very short notes packet. In fact, we'll be done with this by the end of the week, and then your combined test over Units 8 and 9 will be on the block day next week. What we're going to be doing is looking for how do we make inferences about scatter plots. So, in Unit 3, we did a lot of work with scatter plots, but we didn't do... But we kind of just accepted that the slope of our line was the slope, when in reality, when we have a scatter plot, the line that we calculate is done from a sample of points, and therefore is not perfect because samples are not perfect. And so just because we get a line of best fit, even with a strong correlation, does that mean necessarily that there's a relationship between our two variables? So the first thing I want to point out that is whenever we have a line, like the slope is really a description of the relationship between two variables. How they change together. So if we're trying to decide, is there a relationship between two quantitative variables, what we really need to do is say, is the slope a significant slope? Whereas like all that chi-square stuff that we did the last couple weeks, is there a relationship between two categorical variables? This is there a relationship between two quantitative variables? So what you have here is a population line, in that this is all of the eruptions of Mount Faithful over a 1 month period. And so for each point here is, the X is how long that lasted. The Y is how many minutes there had been previous to that eruption. So as you can see, the eruptions that lasted longer had a lot of minutes beforehand, okay? So now imagine, so there's 222 points on the scatter plot. Imagine we only took a sample of 20. And there's lots of different ways, like this one, it's a lot easier to see on my graph. You can see the colors here. But imagine we pick just these 20 points. And then, so we can see that the equation for the line of those 20 points had a slope, the slope was 10.2. Whereas these 20 points have a different slope. These ones have a slope of 7.7. And these 20 have a different slope of 9.5. Okay? And so in these particular cases, we have 3 different samples, 3 different slopes. Now, all of them are kind of close to our population slope of the 10.36. So now imagine, so we're trying to get a feel for, if I took a large number of samples, not a lot more than 3 samples, what would the distribution of the slopes look like? So if you turn the scatter plot, it should be linear, right? So if I look at this set, this looks like a linear set of page. I have the equivalent of me taking a very, very large number of samples of slopes using some of my fancy programming. Okay? All right, so this is from that previous group. So I want to point out that the shape, it does seem to be approximately normal, which is something we like. Okay? That the center, it's kind of hard to see, but the center of these slopes, by the way, this is new. So we had mu as the population mean, and that correlated with x bar. We had p correlating with p hat. Okay, so our population slope, we use the symbol beta, and the sample slope is b. Okay, so the center of those sample slopes, because those are the slopes of all the samples, happens to be about 10.36, which was the slope of the population line. As for the spread, we can kind of get an approximation here. Probably the easiest, I would say that this seems to be like 14.8, and this seems to be like 5.8. And I don't know if you, so the distance from these guys is 9. And keep in mind that should be 1, 2, that should be 3, that gets just about everything, which for a normal distribution, that 68, 95, 99.7 rule, so just about everything was 3 standard deviations on either side. So if I take that distance, and so I get 9, and I divide that by 6, because 3 standard deviations this way and 3 standard deviations this way, we can see that it's approximately 1.5. And there's formulas for the standard deviation of this on your formula sheet, but really, you don't even need to worry about those, okay? So, when we're doing all this inference for beta, so we're trying to use B to conclude about beta, so that's an inference for beta. Okay? We're going to use the same set of the same conditions for both either a confidence interval or a test, and those conditions exist in the word liner. Okay, so essentially, the conditions that need to happen is, the first thing is that when we look at this data, it doesn't make sense to make an inference for slope if things aren't linear. Okay, the observations need to be independent. That should feel pretty good to you guys, or familiar to you guys. It's going to be the same idea. Typically, it's going to be 10% condition here. Okay, now, the normal distribution is still there, but what needs to happen here is that the residuals need to be normal. So, a real quick reminder of what a residual is: if this is my scatter plot, and I sketch a line, that is the best fitting line. The residual for a point is essentially this distance. You will get some sort of graph, so that would be the residual for this specific point. Residuals that are below the line are negative, and they're calculated by doing what actually happened minus what was predicted to happen by the line. So when we check for normality, we want to check that the residuals are normal. And then equal variance, and that's what I'm going to kind of sketch over here. What that really means is we see no weird fanning on either the scatter plot, or more likely we're going to look at this at the residual plot. We'll kind of go into some more details with the actual example I do on the next page. And then, of course, always we need to have data that comes from either a random sample or a randomized experiment. So let's go ahead and look at a true example, okay? I know it's been a long time since we talked about some of these things. So the way we do this is you're going to use the sample slope plus or minus a t star. That t star is going to be the same way we've always done this, where we kind of graph t. We label our degrees of freedom, and we find that middle chunk, okay? So, and then the standard error, and this is always going to be given to you in the data analysis, like where you find your slope is where you're going to find the standard error of that slope. So, to look at this example, perhaps fidgeting, another non-exercise activity, explains why some people may spontaneously increase non-exercise activity when fed more. In other words, if you feed people more, will they become more fidgety? Okay? So they measured how much energy they gained compared to how much energy they used by feeding them more. Okay, so let's go ahead first and foremost. In this particular case, we're doing a confidence. They want 90% confidence interval, so we're gonna construct a t interval for beta, where beta is equal to the slope of the true line relating NEA change, and fat gain. All right, and you'll notice that they give us the raw data here. They just gave it to us in two rows, but it's still just one long table. We have a scatter plot. We have a residual plot. We have a histogram of the residuals. Okay, so just to kind of make some sense of these graphs, to do some reminders, as we look at this, I can look at, say, this point right here that has a residual, so that particular point is half a unit above the line, or just under half a unit. You can see this point right here has a much larger residual. It's magnified here. So essentially, the residual plot shows us this kind of magnification. And some of the things we learned is that if there's no pattern on the residual plot is a good thing. It tells us that the line is an appropriate model. Okay, and we can see kind of when we talked about no fanning, as I look at this, it seems to be kind of equally scattered through. Okay, by the way, this one residual here is probably this one right here on the table. Right, it's the one where or on my histogram, it's the one with the really big residual, but most of the residuals are really small. Okay. And so you have some positive, some negative for the ones close to the line above and close to the line below. So just kind of making some sense of that. So let's go ahead and check our conditions. So essentially you're always going to, you can check each of them kind of the same way. Because I give you so many graphs, like one of the things that you're going to want to do is make sure you're specific about which graph that you're referencing. So the first thing we want to ask ourselves, the L stood for linear, and there's essentially two ways I would accept you checking this condition. The first way is to look at, say that there was in fact no pattern on the residual plot. Because that tells us that the line was an appropriate model. The other one you could have put, if you wanted to, was a linear pattern on the scatter plot. All right. Independent. 16 is less than 10% of young adults, healthy young adults. Normal, the residuals show the histogram, so you're going to talk about which graph? Histogram of the residuals. Is approximately normal. Okay, equal variances. So we kind of said before that means no fanning in the residual plot. I kind of want to show you what fanning might look like. So for example, if we see this where there's greater variability on the right-hand side of the graph than on the left-hand side of the graph, or vice versa, like the variability should be equal above and below the graph all the way through the x-axis. So we're going to say no fanning on the residual plot, but I wanted to make sure I pointed out what that might look like. And usually what fanning represents is maybe a different type of model that we should be looking besides linear. And then, of course, the last one's the easiest one. We were given above, I believe. Yep, we were given a random sample. I'll give you guys a second to get that down, because that was a lot really fast. So as with any test, the first box we are going to define our procedure. That's what the t-interval was. Notice that I said for beta, and this is why we always do a t-interval for mu, or a t-interval for mu1 minus... We always say but what it's for, because you can do them for different things, along with checking our conditions. So our next box is going to include our calculations. So we're estimating the slope, so we got to go back and we got to remember, how do we get the slope from an equation set, or from one of these boxes that we have up here? And the answer is you look for the coefficient, and you want to do the coefficient of the x variable. So we can see from the graph our x variable is NEA change, so we want the coefficient of the NEA change that we have right here. So our b is going to be negative 0.00344. Okay, and in this case, we have to find t star. We haven't done t star by hand in a really long time. In this case, our degrees of freedom. Well, when we do these, guys, our degrees of freedom is our sample size minus 1. So in this case, or I'm sorry, sample size minus 2. I kind of like to think of it, when we had one variable, we subtracted 1. When we have two variables, we subtract 2. So our degrees of freedom in this case is going to be 14. And if we want to be 90% confident, the area of our tails is going to be 0.05. Now, to find that t star, and there is a calculator shortcut to do these, but I'm pretty sure in order to use the calculator shortcut, you actually have to type all the data in. So we're not going to use the calculator shortcut because it would be too tedious. So if we so what you would need to do is go into inverse t in your distributions menu. So second vars, choosing option number 4, inverse t. You're going to give it that right-hand area of 0.05. It's going to ask you for degrees of freedom. You're going to give that 14. And what you find is that your t star is 1.76. Negative 1.76, but in reality it's both. And what we do with that t star is our margin of error. So our estimate is negative 0.00344. Then we do plus or minus our t star, which is that 1.76 that we just got from our calculators. And then we're supposed to multiply that by the standard error of our slope. Well, the standard error of our slope, if we go back to our box, if this is the coefficient, this is the standard error of the coefficient. So this 0.000741, this is my standard error of my slope. All right, excuse me. So to find our interval, you're going to do negative 0.00344. Oh, I have all these things in my calculator. Hold on. So you're going to do negative 0.00344 minus what? I know you guys can't see my calculator, but it's here. So all I'm doing is plugging the minus side of this into the calculator first, and I've got negative 0.0047. And then I'm going to do the same thing, only with a plus sign in the middle. And I get negative 0.0021. So hopefully this is giving you guys kind of a vibe about how we calculate these. And it's a nice little review of, you do your statistic plus or minus your critical value times the standard error of that statistic, if we had to go back to doing these by hand. Okay, and then the last thing we need to be able to do is make a conclusion from these tests. So, as all confidence intervals start with, we're going to go, we are 90% confident. That the interval from negative 0.0047 to negative 0.0021 contains the true slope of the line relating NEA change and fat gain. Okay, so I know this feels like a lot of information, but in reality, it's a lot of what we've always done in terms of confidence intervals, where you have your point estimate plus or minus your margin of error. Okay, some other things I want to point out is what does it mean for there to actually be a relationship? Like when I see that this slope, that the essentially, if there's a relationship between two variables, the slope has a sign. Okay, so a scatter plot where there is no relationship would be a boring one, right? It would have, there would be no inclination whatsoever. X and Y would change independently of each other. So as X increases, Y stays about the same. Okay, so the fact that this entire interval is measured in is negative suggests that there's a negative relationship here. And even though these numbers are close to zero, there's a lot of things that can make those numbers. I could change this exact data set, but if instead of measuring the fat gain in kilograms, I measured it in grams, we would see a much larger slope, right? We would see that this would be like negative 4.7 and negative 2.1. So it's the fact that the interval is negative at all says that there is a significant relationship between these two variables, that increasing one decreases the other. So hopefully this is a good start for Unit 9, and I'm hoping to be back to talk to you guys on Thursday, probably.